So, picture this, a car that can see perfectly, even in complete darkness. Or, a robot that never gets thrown off by super fast motion. That's the whole promise of this new kind of camera technology. But there's a pretty big catch. It sees the world in a way that's just totally alien to the cameras we're used to. So today, we're going to dive into some really groundbreaking research that's finally teaching these two totally different eyes how to see in 3D together.
Okay, so what you're looking at here, this kind of psychedelic landscape, that's a depth map. It's basically how a computer sees in 3D. Now, normally you make one of these by comparing two similar pictures, kind of like how our own two eyes work together to give us depth perception. But what happens if one of those eyes is just a regular camera, but the other one is something totally different? Something that speaks a completely different visual language? How on earth do you get them to create a single cohesive 3D picture? It's a real head-scratcher.
And that right there is the core problem. It's called asymmetric vision. And for things like self-driving cars or advanced robotics, this is huge. We desperately need to combine the strengths of different sensors. A system that can see in any condition? That's the holy grail, right? But the question remains, how do you get two eyes speaking two different languages to agree on what they're actually looking at? Let's get into why this is just so tough to pull off.
All right, here you can see the problem, plain as day. On the left, you've got your standard camera image. It's rich, it's got color, texture, all the static details. But then look at the right. That's the exact same scene, but seen by an event camera. It's sparse, right? Almost ghostly. All it's showing you is motion and changes in light. So how could a machine possibly look at a specific, detailed pixel on the left and match it to just a flicker of light on the right? It seems impossible.
So what even is an event camera? Well, it's pretty cool, actually. It's inspired by our own biology, by our retinas. Instead of taking picture after picture, like a movie, each individual pixel acts like its own tiny neuron. It only fires off a signal when it sees the brightness change. This makes them unbelievably fast. We're talking microsecond fast, so they have zero motion blur. And they're amazing in low light. But, of course, there's a trade-off. You can see it right there. They're missing all that rich, static context you get from a regular camera. And that brings us right to the heart of the problem. To get that 3D depth map, you absolutely have to match up the same points in both views. But how do you match a detailed pixel with just a blip, a flicker of light? This massive mismatch, what researchers call the modality gap, is the puzzle that has stumped this entire field for years. That is, until now.
So to solve this huge problem, a team of researchers came up with something they call BCMPS stereo. It's a brand new framework, and it's not just about mashing the two signals together. No, it's about actually teaching these two very different cameras a brand new shared language so they can finally understand each other. Let's dig into how they did it.
Yeah, the whole idea here isn't just to, merge the two streams of data and hope it works out. It's way, way more sophisticated than that. The real goal is a much deeper kind of translation. It's about teaching the data from one camera to literally think and act like the data from the other one. That way, you create a true common ground where you can actually compare them.
Okay, so the Bixby Imperio solution really boils down to two key parts that make all this magic happen. First up, it has to get those two different visual languages aligned. And to do that, it uses this really clever module that we can think of as an accent coach for the data.
So this accent coach has a technical name, of course. It's called the Cross-Domain Embedding Adapter, or CDEA for short. And its entire job is to take the data from one camera, say that sparse stuff from the event camera, and basically remap it so it mimics the style and structure of the data from the regular camera.
So how does this accent coaching actually, work? Well, the CDA essentially forces the features from both cameras into a shared framework, a common language. It takes that sparse, motion-based data from the event camera and projects it into the exact same feature space as the dense, textured data from the standard one. And this deep alignment, that's the breakthrough. It means that for the very first time, a simple point of motion can be directly and meaningfully compared to a detailed pixel. And that is the secret sauce for getting accurate 3D matching.
But hold on, what if this accent coach is too good? What if, in the process of translating, it loses important information? Forcing one type of data to act like another could accidentally smooth over the very details that make it so useful in the first place. Well, to stop that from happening, BCMPS Stereo has a second absolutely critical component, a quality check to make sure nothing gets lost.
Yeah, anytime you translate data, there's a risk you'll lose something. So to fight against that, the researchers built in this brilliant little mechanism called the stereo canonicalization constraint, or SCC. Just think of it like a super strict quality control inspector that's watching over the whole translation process.
And the way the SEC works is pretty ingenious. So, after the accent coach does its thing and aligns the data, the SEC throws down a challenge. It tells the system, okay, now take this newly translated data and use it to reconstruct a perfect, high-quality image. If that reconstructed image comes back flawed, if it's blurry or missing details, the system knows it lost important information during the translation, and it gets penalized. This pressure forces the whole model to learn a translation that keeps the best, high-fidelity information from both cameras. No cutting corners.
All right, so the theory sounds great, right? An accent coach and a quality check. It's a really impressive idea. But does this two-part system actually work in the real world? Let's take a look at the results and see how BCMP stereo stacks up against what came before.
And wow, the results are pretty striking. In each of these pairs you're seeing, the old method, called ZEST, is on the left. And on the right, that's our new system, bi-cam stereo. Just look at the top row, the daytime scene. See how much sharper and cleaner the details are on the car and those poles? And that same huge improvement is just as clear in the much tougher low-light scene down below. It's not even close.
So, what does this visual upgrade actually mean? Well, we're seeing way cleaner boundaries on objects and much more accurate depth readings, especially around tricky things like cars and streetlights. This is the proof, right here, that the accent coach and the quality check are really working together. They are successfully bridging that modality gap we talked about, and the result is a much richer, more accurate 3D view of the world.
This quote from the researchers really just nails it. It gets to the very heart of what they accomplished. See, the challenge was never just about translating the data from one form to another. It was about doing it without, as they put it, information lossy marginalization, which is a fancy way of saying without throwing away the unique strengths that each camera brings to the table. And because they figured out how to preserve all that critical information, their system just hits a whole new level of performance.
So by teaching two totally different ways of seeing to not just get along, but to actually make each other better, this research takes a huge leap forward. We're talking about a major step towards machines that can see the world with a kind of superhuman robustness. And with vision this powerful, you have to wonder, how soon until our machines can safely navigate any environment, anytime, day or night? Thanks for joining us for this explainer.